Okay, so if you have your eye clicker, I think there are maybe 5 questions. Most of them are pretty quick, so I'll give you a little time. The ones that I think you need a little bit more time, I'll give you a little more. So that's the first question. That's a straightforward one, so I'm going to just give you a few seconds. 5, 4, 3, 2, 1. That's why you have to get here on time. 0. Okay, in the context of fluid mechanics, the amount of mass in a system is constant, true or false? Yes, it is true. What's another name for a system in fluid mechanics? Control mass. It's a good one. Control mass. Okay, the next one. In steady flow, the mass flow into a control volume equals the mass flow out. True or false? And I better click this. Okay, so and this will be quick. You're already answering. 3, 2, 1, 0. In steady flow, the mass flow into a control volume equals the mass flow out. Yes, indeed true. All right. Okay, in the derivation of the Reynolds transport theorem, the normal unit vector n, pick one of those answers. Quickly look back into the notes from the last class. So 5, 4, 3, 2, 1, 0. Yes, it points outwards. Okay, the quantity del, oh, there is a typo. Let's keep that one. No, there is no typo, hold on. It's just that this vector bar makes it look like a delta, like a del. But this is just V with a vector bar on top, all right? This is just vector V on the left, so I'll go ahead and do it. So the quantity V dot n represents A, B, C, or D. Okay, 3, 2, 1, 0. Okay, so let's see. Yes, it's a normal component, right? Okay, so far so good. Okay, in applying the Reynolds transport theorem to Newton's second law, the generic extensive property B that was used to derive the theorem should be chosen as A, B, C, D, or E. 3, 2, 1, 0. Yes, linear momentum. Okay, so most of you are on the boat. Last one. Quiet, please. Last one. Air flows through a doorway at an angle alpha, as shown here. which of these expressions represents the mass flow rate? The question is not there, but I'm telling you. Which of these expressions represents the mass flow rate through the opening? Mass flow rate through that opening. 3, 2, 1, 0. And that is correct too. Right, the sign, that's what gives you the normal component of the velocity, right? That's related to the previous question. So you need the normal component of this velocity. That would be v sine alpha. So B was correct. Okay, enough of that. Okay, so at the very end of the last lecture, we were talking about the Reynolds transport theorem and how to apply it to the second law, Newton's second law of dynamics. So some of this we already did last time. So we picked, this was one of the questions today, we picked B, the extensive property, to be the linear momentum for our fluid element. And therefore that makes lowercase b, the intensive property, just the velocity. So we arrived at this equation. The left-hand side has the variation in linear momentum of the fluid element. Remember, the fluid element is our system, or the material that is inside the control volume at time t equals 0, for example, or at the time that you're looking at it. That's your system. And so the left-hand side is the change in the linear momentum. We know if we skip all the middle, we know from Newton's second law that that has to be equal to the sum of forces. So the left-hand side equal to the far right-hand side is Newton's second law. And of course, what's in the middle is what comes from the Reynolds transport theorem, which is the two integrals, right? The integral over the control volume, which is differentiated in time, and then the integral over the control surface. So by now, you probably know this, but if not, let's make sure you do. The meaning of those terms. The first integral is a time rate of change. It's a time derivative, so that's where the time rate of change comes in. And what's inside, of course, is the integral of all the linear momentum inside the control volume. So you take rho times v times differential volume. That's the linear momentum of a small piece inside the control volume. Small volume, small differential volume, you integrate it as the whole linear momentum. And then the second integral is what comes from the flow through the control surface. And of course, that's the flow of linear momentum through the control surface. It's actually, we can refer to it really as the net flow of linear momentum through the control surface. So that's more or less where we left it. And that's the general, you were asking earlier, what, is the general versus the, what they call simplified or specific, particular versions of this relationship. This is the general one. It's the most general. Now, in many problems, in fact, in most of the problems that you address using this equation, there are many times that you end up simplifying things to make it a little more tractable. So there are many problems there is the control volume. There are many problems in which the flow through the control surface occurs only at very definite places. Right? So if I think of a practical apparatus, like a turbine or a pump, there is a place, there is an area, a section of the total control volume where the flow comes in, and there is another area where the flow comes out. That's only if there is one flow in and one flow out. But in general, there will be a limited number of places on the control surface where the flow goes through. So I shaded two arbitrary spots there, and so we could say that only through those spots is where fluid goes through the control surface. Most of the control surface is close to the flow, because if it's a real device, it'll be the walls of the turbine or the pump or the compressor or whatever it is. So the flow is only happening through some spots. So what that means, of course, is that this integral that is over the control surface, I can always break it down into integrals for each of those areas. So I can take the entire integral, which is here on the left, and say that it's just a sum of integrals for each of the patches that are shaded. And I may have more than two, so maybe I label the first one A1. If this is A1, I have the integral over A1, and then I would have plus the same integral over A2, plus the same integral over A3, until I get to the last piece through which there is flow. Again, many of the devices that we look at have one inlet and one outlet, so there would only be two such areas. So therefore, you would break it into two integrals. Okay, so also, and this was also on the quiz just now, on the questions, this is also true. Yeah. So if I'm looking at one of those patches, I know that V dot n gives me the normal component. So in brown there, you see the actual full velocity vector on that spot, and the normal unit vector. If I do V dot n, then I get the component of the velocity vector along the red unit vector. So we know that. And of course, that appears, going back to this, that appears in those integrals, right? I put it in parentheses, the V dot n terms. That's the normal component of the velocity. So now let's simplify it a little more. Let's take it a step further. Suppose that to make our life very easy, on that area through which the flow is going on the surface, let's suppose that the density and the velocity are uniform. That is, they are the same everywhere on the patch. They don't vary. There is not a profile of velocity, but it's all the same. Or I can make the assumption that it's all the same. And further, I make the assumption that the patch of area through which there is flow is flat. It's just a flat entry. And again, if you think about simple devices, or devices that we analyze in a simple form, we always think of the place where the flow is coming in as a flat cross-section and the flow is crossing through. So if I make all of those assumptions, what happens to that integral? Let's put it like that. Since everything is independent of the position on the area, I can take everything out of the integral because nothing changes across that area. So I take the density out, I take the velocity out, I take V dot n out, but I take what it is, which is V sub n, the normal component of the velocity. And then, of course, all that there is left inside the integral is the dA, and that integrates to A. So here is a simplified version of the flux term in the Reynolds transport theorem for such an area. It will just be rho times the velocity as a vector times the normal component of the velocity times the area. But of course, I also know that through that spot, the product of density times normal velocity times area gives me the mass flow rate. That was the last question on the iClicker set of questions, right? Take the normal velocity times the density times the area times the mass flow rate. So my integral really boils down to this. This integral, I didn't repeat it here, but this integral of rho velocity v times v dot n times dA boils down to just m dot v. That's a simplification with all the assumptions that we made. Realize that this term is a vector. Right? The product of the mass flow rate, which is a scalar, times a vector, gives me a vector. Another thing I should tell you, I didn't tell you earlier, so let me flash this equation back for a second. This equation is a vector equation. Newton's second law is a vector equation. Sum of forces equals MA. The forces are vectors, and so is the acceleration. So if you start to think ahead, this equation as a vector equation is really three equations, because you would have to write a component in the x direction, a component in the y direction, and a component in the z direction. So we're looking at a vector equation. So when we come back to our term here, which represents, again, the second of the integrals, is a vector term. Right? Okay, let me stop here for 1 second and see if somebody has a question. I gotta make sure that all these concepts are clear. Any doubts? Nope. Okay, so let's make more assumptions to see how in addition to what we have done, if we can simplify it even more. A common assumption in many of the problems that we look at is that the flow is steady. Right? So if the flow is steady, what happens? That means, again, if I'm looking at the control volume, if I'm looking at my device, I'm looking inside of my control volume, it's always the same picture. It's not a time-dependent picture. And therefore, since I'm taking the derivative of what's going on inside the control volume, that has to be 0. That's always true for a steady problem, that the first term in the Reynolds transport theorem, the first integral, since there is a time derivative involved, has to be 0. So going back again to this equation, I'll return to that one. Any steady flow will have this term be 0. That's one good thing to remember. Right? If the flow is steady, this time rate of variation inside the control volume has to be 0, or integrated over the control volume has to be 0. So we were here, right? No. Yeah, we were here. So if the flow is steady, I can say that. That's correct, the correct thing to write. So Reynolds transport theorem, in connection to the second law, for a steady problem is just this. That's the same equation as before. I just knocked out the transient term. It just says that the sum of forces acting on that control volume has to be equal to, remember, this term is the flow, the net flow out of the linear momentum through the surface. It has to be that, because the first term in blue has been put to 0. Now let's not forget mass conservation. The first equation that we looked at with the Reynolds transport theorem. If I looked at mass conservation in a steady flow case, all I have is that. For a steady flow, the integral over the control surface of rho v dot n dA equals 0. This should be obvious to you, because what is a description with words of what this term is telling me, this last term? Tell me what this is with words, a simple textual explanation.
Flow in equals flow out.
Yeah, that's a very simple one. Flow of, what flow? Mass, right? Mass flow, it really says that the net mass flow rate out of the element is 0. Because remember, that's what the term represents, is the net flow out. Of course, net flow out is mass flow out minus mass flow in. So to say that the net mass flow rate out is 0 is equal to say that the mass flow rate in is equal to the mass flow rate out. That's what this equation. So in a problem, I usually have to deal with these two equations. So now let's put all of these simplifications together in one place and see what happens. In many problems, we can assume steady flow, or we are told, or we are interested in looking at the steady flow situation. In many problems, there is only one inlet and one outlet for the device. And if you make the assumption that over the inlet or the outlet, the flow is uniform, that is, you don't look at variations of velocity or density across the inlet or the outlet, then let's say that we label the inlet 1 and the outlet 2, then of course mass conservation is just that, right? M dot 1 has to be equal to M dot 2. A very trivial statement. Remember again, it came from here, right? That's what this was originally, but when we made all those assumptions, it just becomes M dot 1 equals M dot 2, and because it's the same, I can just call it M dot. That's the last term. I don't need to call it M1, M dot 1 and M dot 2, I just call it M dot. And then if I now look at the momentum equation, or the Newton's second law, with all the simplifications that we put in, then we can say that the sum of forces is M dot 2 times vector V2 minus M dot 1 times vector V1. Those two terms, of course, came from here, these integrals. Right? So it's like I only have two of these integrals because I only have two areas. And with all my simplifications, they just become, for the one area 1 says, or area 2, which I wrote first, because I'm assuming that's the outlet, that's positive. M dot 2 V2 just comes from here. And then negative M dot 1 V1 would be for the other area where the flow is coming in. Where does the sign come from? Because in these integrals, these are all plus, 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 plus. Each integral is a plus. So where does this minus come from?
Cross product of the velocity and the normal effect?
Not cross, but dot product, right? The dot product of V dot n. Right? The dot product of V dot n gives you V sub n, the normal component. It'll be positive if it's flowing out. It'll be negative if it's flowing in, if the fluid is going in through the surface. So that's where the sign comes from. So, but that's what you get, M dot 2 V2 minus M dot 1 V1. And because we said earlier in mass conservation that the mass is the same, then you can factor it out, M dot, just V2 minus V1. I would argue that this is perhaps the simplest form of the Reynolds transport theorem for mass conservation and Newton's second law. Keeping in mind always that this second equation is a vector equation. So it really represents three scalar equations. It's really all those three, right? You write the equation in the x direction. Of course, M dot is M dot as a scalar. M dot is the same for all three. But the components of V2 and V1 in x, y, and z, we have been calling u, lowercase u, lowercase v, and lowercase w. So those are the three components. So I think that's pretty much what your question was at the beginning. The most general form and perhaps the simplest form of the equations. Anywhere in between there is variations depending on which assumptions you don't make. If I remove some of the assumptions that I made here, right, then, whoops, you don't see those now. If I remove any of those assumptions, then I have to go back and revise something because this simplest version of the equation has all of those assumptions in. All right? Does anybody have a question now? Everything is clear? Smooth? Transparent? No question. Okay, so let's, I'm sure there are questions, but that you just don't want to ask. Let's look at a very simple problem. Let's take this out of here. Simple practical problem. Suppose that I want to find engine thrust. So I have an engine and I want to find how much thrust how much thrust it generates. So I would take my engine, put it in a test stand, bolt it to the test stand so it doesn't go away when I run it, and I run the engine. So typically this is what would happen. With the engine running, in steady state, there would be flow coming in from the front, and that flow would be characterized by a certain temperature, pressure, the area of the inlet, and the velocity. I call it lowercase u1 because I'm putting it all in the x direction. I'm saying the x direction is the horizontal direction, and that's where the flow is. So then I have an outlet. I have a pressure there, also an area, and also a velocity. And then I have atmospheric pressure, say, surrounding the engine everywhere, except where those pressures might be different, as indicated here. So the P1 is here, the P2 is in the back. Everywhere else is P0, atmospheric pressure. So I want to find the thrust. So that's, of course, an application of my Reynolds transport theorem equations for conservation of mass and conservation of momentum. And I just wrote them again here in the general form. So you probably don't need to write all those equations again, except for the fact that the more you write them, the more you remember them. So, but there they are. And then I say, okay, what assumptions am I going to make? Precisely the ones that we just used in the derivation. So let's say it's a steady flow, the engine is running continuously. Take that the flow through the inlet and the outlet is uniform. That's already indicated in the diagram, for example, for the velocity, because you see that the velocity arrows here are uniform. And go ahead and simplify. So we just go through the same exercise that we did a moment ago. Conservation of mass equation, which I call C, for continuity. That's another name for it. It's probably a good time for you to know that. The equation of conservation of mass is known generally in fluid mechanics as the continuity equation. So when somebody says continuity equation, they just mean conservation of mass equation. So I call it C for that reason, for continuity. So that's the equation that we just saw. The mass flow rate in, rho 1 U1 A1 equals the mass flow rate out, rho 2 U2 A2, and we call it just m dot. So what else can we do here? Well, notice that we were not given the density at the inlet, but if we take that this is air that is flowing in, then I say, well, if that's air, I'll use the ideal gas law to get the density. That's what I did there. So I can get the inlet density, rho 1, because I was given the temperature and the pressure. And I get the missing density. So now when I write the components of this equation, I realize immediately that I only have to worry about the x components. So remember, I told you this is a vector equation, x, y, and z, but this problem is so easy that everything is in x. So all I do is write the x component. And there it is, in simplified form already. So rho 1, u1, u1 again, right? Because that comes from here, right? The v dot n gives me u1, but the component of the velocity in the x direction is also u1. That's why you see u1 twice, right? I put them separately because in many problems it's not as trivial as it is here, and it is better to look at them separately. You need, remember, you look at the integral, you need the normal component and then the velocity. So the normal component in this case happens to be equal to the velocity at that point, or the component of the velocity. So the inlet comes out negative, of course, because it's flow in. The outlet comes out positive, and that's the sum of forces. So that's my equation. So, and of course, if I use the fact that rho 1, u1, A1 is m dot and is the same as rho 2 U2 A2, then of course m dot is the same. I can factor it out, and I would get the same equation that I got before. If you remember, let me put this back here. all I'm getting is the first of these, right? M dot U2 minus U1. So we just pretty much did the same thing that I did in the derivation. All right, so that's the left-hand side. And so now we need to deal with the forces. So, and remember, this engine is right there. And I told you is, if you don't attach it to the test stand, it will go through the wall if it's running, right? Because it'll have thrust. So you have to fix it down. So what are the forces that are then acting on this engine? Can you tell me? Say that again? Pressure? Pressure is not a force, but there is a pressure force. What else? Gravity is in whatever direction you want to put the gravity in. Let's put it in this direction so we don't have to worry about it. Right? So the weight of the engine, of course, goes down. I'll have to build the stand strong enough to hold the engine, but that's not important here. We're talking about horizontal direction. What other forces besides pressure forces? Yeah, the force that you need to put there to hold the engine in place. So if I write it all out, the best way to look at this is to look at it this way. Sum of forces. So notice that I have created a slightly different control volume, just because that's one way to look at it. That has to do with the pressure forces, the way to calculate the pressure forces. But let's first think about the force to hold the engine in place. That's what I call there F sub T, is the second one. So obviously that should be a force to the right, but if I get it wrong, I'll get a negative sign in the answer. But so I need a force there, F sub T, which I don't know what it is, to hold the engine in place. And then there is the pressure forces there. So let's see how I came up with those values. P1A1 is easy, because A1 is the front area, the inlet, and so the pressure there times the area of the inlet gives me that force. And then this one, so and I put it positive because it points to the right, and that's the positive x direction. This one, minus P2A2, is also straightforward. Minus P2A2, because that is the force, the pressure force right here on the outlet, where the area is A2, the pressure is P2. But what about the last term, minus P naught A1 minus A2? How can you justify that term? Where did this come from? That's a good way to look at it. That's probably the best way to look at it. You have to step back and think of statics, right? On the curved portion of the engine, right? On the curved portion of the engine, if I'm looking at the horizontal force, how do I find that horizontal force? Right? So this is straight back to chapter 2. You know, how to find the horizontal force on a curved surface. And then you find the force on the projected area. And the projected area is, of course, that's why I drew these additional dashed lines over here. The projected area where P naught acts is a ring, right? Because it's the big inlet circle minus the small outlet circle. So the area that is left is A1 minus A2, inlet area minus outlet area, and it's acted upon by atmospheric pressure. So that's my equation that has all the forces in the horizontal direction. So then, of course, you can solve by putting that together with the previous equation. So this, all these terms equal to m dot u2 minus u1, so that's right there. And then solve for the force that you need to hold the engine in place, which of course is your thrust, right? So, so that's it. And then if you wonder what the numbers would be like, then you can just put in some numbers. And I just put some numbers here as an example. Inlet velocity 200 meters per second, outlet velocity 500 meters per second, inlet pressure slightly below atmospheric pressure, 80 kilopascals. I put the outlet pressure same as atmospheric pressure, so I put P2 100 kilopascals, same as P naught. Inlet area 1 meter square, and the inlet temperature that, remember, you need it for the density. So if you plug everything in, you get your density, you get your mass flow rate, happens to be about 200 kilograms per second. And then you put everything in the equation, and you get this, about 82 kilonewtons. Yes?
You wrote some of the forces. Can you explain?
Right above there?
Yeah, the line above FT.
Yeah. Or even before that. Right there.
The directions you chose for P1, A1, it doesn't depend on the flow of P1, at P1?
It doesn't depend on the flow, no, because that's the atmospheric pressure acting on the inlet surface. Yeah. So it's like a static calculation. So the fluid is on the left. The force has to be to the right, right? For A1. For A2, the fluid is on the right. The pressure force would be to the left. Right? So it's just a basic static calculation. Where is the fluid? If you're computing a pressure force, where is the fluid? Then that tells you the direction of the force. So that's the reason for this plus and this minus. And of course also this minus, because the fluid is to the right of this curved surface. Right? So therefore the force is to the left. Yes?
So that term there, the atmospheric pressure times difference in area, is that like conceptually kind of like the air resistance?
Conceptually like?
Air resistance? Like,
No, this is not air resistance whatsoever. It's just static pressure. Static pressure. This engine is not moving, right? It's sitting on the stand. So you could argue that there, if there is some currents outside, that you have to figure that in, but we're not including that. We're thinking the engine is standing on the test stand. There's flow in, flow out. The air around it is more or less quiescent, which is not 100% true, but so this is just all these pressure forces are just static pressure forces. Static pressure, nothing to do with motion. All right, so we get that number. Realize that the 61.9 kilonewtons came from the actual term that generates the thrust, which is the m dot U2 minus U1. This 20,000 come from the static pressure forces. It's not insignificant in using these numbers, but of course this is the important one. Okay. The 61.9 is where you're generating by putting the fluid through the engine. Any other questions? Yes?
Are we able to use gauge pressure so that P naught goes to 0?
Well, in fact, that is, let me see. In fact, I was going to say that is, you can rearrange this in terms of gauge pressure, because if you combine these A's, you get P1 minus P naught times A1, right? And then if you combine the two that have the A2, you get minus P2, I'm sorry, minus A2, and then should be P2 minus P naught. So you could combine it that way, and then you have gauge pressure. And therefore, you wouldn't have to worry about that. But you have to come up with the same result, of course. Any other questions? Okay, let me see. I only have I still have about 9 minutes to show you another example. A little bit more complicated, or complicated in some other ways. So here's another problem. It has a few more things in it. There is a flat wall there, at an angle. This is a solid wall leaning at an angle theta with respect to the horizontal. And there is a jet of water, a horizontal jet of water that is hitting that wall. And for simplicity, we are assuming that it just diverges into two jets. So there is a jet that goes up the wall and another jet that goes down the wall. That's a simplification, of course, because if it's a round jet hitting a wall like that, it would not branch out into an upward jet and a downward jet. It would actually have like a fan, right, of water going in all directions. Right? So but we're going to make our life easier by assuming that it just branches into two. That's a simplification, but it's to understand how to use these equations. So we're asked to find what force applied perpendicular to the wall is needed to hold the wall, that flat surface, in place. So obviously, if I don't hold that plate with a force, the jet is just going to push it to the right. And then to also find how much of the mass flows up and how much of the mass flows down. So m.1 is the mass flow down, and m.2 is the mass flow up. All right. So we go through our assumptions. We say we're going to look this as it is steady. So this is continuously hitting the wall, constant density, so I can go ahead and write my equations. So the easy one is continuity, conservation of mass, because I know since the jet is splitting in two, I know that whatever mass flow rate comes with the jet, which I call m dot j, has to be equal to the sum of the mass flow going in each direction. So m dot 1 plus m dot 2. And of course, the mass coming from with the jet is just density times velocity of the jet times the area of the jet. Yeah? That part is easy. Okay, so, whoops. That's good. I shouldn't do that. So now we're going to run. Let me actually. Well, unless we go through the following thinking process, we can't solve the problem because we're not given the velocity of the fluid in either of these two branches. We know the mass flow rate, but we don't know the velocity. So how can we find the velocity of the liquid on each branch of the division of the partition? And one way to do this is by saying, well, let me just concentrate on a small region near the point of impact. So I'm going to concentrate on a small region here so that I'm not really going over very large distances. I can say maybe that variations in height are negligible. And if I do that, then I can think of an old friend. And who is that old friend? Bernoulli. Because I say, okay, so under those assumptions, let's take a streamline that goes from somewhere before the impact point, say on the surface, and follow it along until the jet has divided. So let's say, for example, that you're going to follow it from here, a little before impact, to a little after impact, and the same thing for the other branch. So if we do this one first, so if I decide to follow a streamline on the surface of the jet, right, from a little bit before the impact to a little bit after, what do I conclude from Bernoulli's equation? Steady is an assumption that goes into the Bernoulli equation, and it's also an assumption that we made to solve the problem. The velocity would be the same at those two red dots. Look at the Bernoulli equation with the assumptions that we have just made. The velocity is then the same here as it is here, and therefore is the same here as it is there. I follow two different streamlines, of course, to get to the two places. Right? So convince yourself that the velocity would be the same from Bernoulli's equation. So now I know the velocity that the fluid has after it hits the wall. It happens to be the same under the assumptions. So that's what this is, right? V1, the velocity in the downward branch, is equal to the jet velocity, and V2, upper branch, is equal to the jet velocity. So now I can take my Newton's second law from the Reynolds transport theorem and apply it normal to the wall. So there is my Reynolds transport theorem equation. Maybe I can make this a little bigger. Okay. Sum of forces, the same equation that we have seen before for steady state. Okay. And there is my jet. Maybe that was a little too much. So I'm going to go, my coordinates are going to be parallel to the wall and normal to the wall. That will be the best choice of a coordinate system. So if I go normal to the wall, then think about this. This is where you have to be very careful. Right? So there is my sketch. I'm going normal to the wall. What do I have? I need the component of the jet velocity, right, that is normal to the wall. That's the minus Vj sine theta. Right? It's negative because I'm making positive away from the wall. Right? So that's why that term is. And then, of course, in the V dot n, right, there is my surface. That V dot n is just minus Vj. All right? Minus Vj, because remember, what goes there is the component of the velocity normal to the surface, and my surface is that shaded area there. So that's the minus Vj. Area of the jet, and then on the right-hand side, the force, which is only one, is the force that is holding the wall in place. All right? So that's how you have to be careful when you're looking at this type of a term, when you have to find components. All right? So from there, you simplify it a little bit. You get that the force to hold the wall in place is just pi rho dj squared over 4 Vj squared, the product of the two Vj's times sine theta. And that answers the first question about what the force is. Because I only have 1 minute left, and I'm not going to rush through finding the masses, I will stop it here, and when we come back next week, I'll finish the problem. All right?